Hi, this is Rahul. In this lecture, I am going to discuss about single source shortest path algorithm, which is Bellman Ford algorithms. Right. Before going to Bellman Ford algorithms, I will discuss some backgrounds about the single source shortest path. Suppose we have a graph. You can see this is a weighted graph, and in this graph, why we call this as a weighted graph, because each is having weight. You can see whatever I am marking over here, there is a one weight corresponding to each edge. Now, the functions we represent the weight functions, there is a one edge. Edge is mapping to real numbers. The real number, why I am taking real number? Because the weight can be either positive or negative, or the range of real numbers would becomes minus infinity to positive infinity. Any numbers we can take. So that's why I am just taking map from any age to real numbers, right? I hope this is clear. Suppose if we want to have a path from one node to another nodes, we may have this path, and the weight of the path is just take the sum of all the weight corresponding to each edge which is falling in this path. So if we talk about this path, then the sum of weight will become 2 plus 4 plus 1, that would become 7, right? The weight of path is just nothing, sum of weights on the corresponding edge which is present in the path, right? This is what this is nothing, just a path, right? I hope this is clear. Now we may have different paths, so many paths from two vertices, sorry. Suppose from S to D, we may have one path. This is one path, this is second path, this is a third one. We may have several paths, but out of available paths we have to find out the minimum one. That minimum path will be called as a shortest path, right? Minimum of all the available weighted path, we take the minimum out of available paths from U to V. I hope this is clear. If there is no path between U to V, I means a vertex. Suppose if we take the one example, S to Z, there is a, we cannot reach from S to Z because Z is disconnected with this graph. So that's why the weight of paths from S to Z would become infinitive. I hope this is clear. Now we'll see the variants of single source sorted paths. There is a first variant is where we want to figure out the locations, or we want to search the destination. Suppose we don't know where D is, we need to find out the search out the where D is. Then we may have any algorithms. There we take the shortest path from any vertex to D, right? I hope this is clear. Now a single pair shortest path is another ones where we take any two vertices, or we can say any pair of vertices, and we find out the shortest path between them, right? All pair centers paths means all the pairs of vertices which is present in graph C, and try to find out the shortest path. I hope this is clear. These are the three variants. Now we'll look at the first one. This one says single source shortest path, right? This is a single short path with shortest path algorithm, Bellman Ford algorithm. Now, so before going to more detail in Bellman Ford algorithms, we see the concept or core idea of Bellman Ford. If you understood this core concept, then you will be able to understand the whole algorithm, how algorithms work actually, right? So suppose we have a graph, yes, D, B, C. You can see these are the vertices, and our intention is to find out the shortest from yes to all other vertices, right? Yes to all other vertices, yes to B, yes to C, yes to D, yes to E, like that, right? Let's initialize all the vertices. Let's initialize all the vertices from S to distance is infinity in the beginning, and the parent, if there is no path from S to all other vertices, then at that time we simply initialize the parent means from the vertex V is going to be visited, which is nil. in the beginning. What it means, I'll explain. Suppose from yes to v, there is a, in the beginning there is a no path. Suppose I am disconnecting it, right? There is a no path, and I, in that moment, from s to v, I am just assigning infinity. In the beginning, we are assuming then there is a no path and we are not reachables from s to v, right? In this case, what we'll do, suppose s to d is 0. What it means, source to source distance is 0. E dot d means infinity. What it means, s to e, s to e distance we are assuming in the beginning infinity. F dot d, infinity means s to f distance is infinity in the beginning, we assume it, right? Similarly, what d dot d means, d dot d means destination from s. This is the shortest short form of notations, distance from s to particular vertex, right? Now these are the initialization at the first step. Second is very important, you should know actually. If you are not able to understand, then the whole algorithms you cannot understand. So we'll see, we'll see this relaxation process, right? In this relaxation process, what I'll make you understand. You can see we have one edge, u v is a one edge, right? We are going to relax this edge, and w is just nothing, is a function, the w from real number, right? If w is just a function, weight function, w u v means some any positive number, any real number, right? I hope this is clear. Now suppose you take these examples. U dot d means what? U dot d is something, one is there, right? Why it is one? From s to u distance is d, right? And v dot d is what? From s to v distance is d, right? Now when we pass u and v is to this function, what this function actually doing? Now you can see, if you take this path to reach v, or if you include this edge to find out the shortest path from s to v, then you get the better one, because this was earlier you had, which was the shortest path, weight was shortest path from s to v. By this it was 10. If you include this is, these two is, to getting the shortest path from s to v, the path weight will become 3 only. So what you will do, you will relax it. So what actually mean? V dot d means 10. It is 10 is there, I will write over here, right? 10 is greater than u dot v. U dot d means what? This is 1, and w dot u dot v, this is 2. You can see this condition is true. If this condition is true, what it means? I do update the weight to reach v vertex from s via this one. This one is nothing, just equal to 1 plus 2, that is 3. V dot pi means, you try to understand, we will put vertex u via u, we are reaching v, so that's why we will put u here. What it means, parent of v is u, or means we are accessing v via u. So these are, if you understood this much, then you will able to understand complete algorithm. Now one more things, what Bellman Ford algorithm detects, it is very efficiently, it can detect the negative cycle if it is present in the graph, right? Let's see how this algorithm actually works. So I have this, you can see this is a one matrix, I have made it, and you can see all the vertices which are present. I have written all the vertices over here which are present in this graph. A, S, A, B, C, D, I, right? And from yes to yes distance, I have taken 0. Yes to all other distances, I have taken infinity, right? Once here, this side, I have written all the edges which are present in this graph. You can see over here, right? All the edges which are present in this graph, I have written, right? If we if we introduce this as to a, there is one is, then we change the corresponding corresponding distance from yes to the particular vertex. So if we introduce this or this edge, we call the relaxation function. This function, what this function actually does, this function will update this value a dot t to 1. Why it is so? Earlier it was infinity, and when we relax this edge or we use this x, then this goes to 1. Rest of value you can put infinity, right? Because you have introduced only one edge. Next, if you are using this a to b is, in that case what you'll do, simply the destination only you can change it. You change it. If you pass this edge to this function, what this function actually doing, this function will update b to d. B to d, what it means, I am talking about this cell, is going to be 2. Similarly, we pass one by one each edge and update the weight, and rest of the edges which I have kept the blanks intensely, the value will be always infinitive. Otherwise, if any value other than infinity in the upper row, you simply copy the same value in the next row. You can see I can minus 9 we can put here minus 4, same value, you don't change it, right? And you how many times you do? This is the first iterations you do. Second iterations you can do, so this in Bellman Ford algorithms. And next third iteration, how many times? V minus n times. V is what set of vertices which are present in this graph G. And next last iterations, if you see any change in the shortest path from yes to other ones, or you are able to relax the edge, what it means, in the vth iterations, this last two iterations, if you find this instruction has been executed, what it means, you will assume that there is a negative cycle, right? I repeat again, in these iterations, if you see any relaxation happened or any change happened to the destination from S to the any particular vertex, then you assume that there is a negative cycle. So if I write the whole algorithm is simple. This is initialization, this is the relaxation of age, and I will write like a algorithms. It is very simple. First relaxation, you can see this is the first one relaxation I have written over here. Now for each for up to in this second is lines, what we will go from 1 to v minus 1. So and for each is we do relaxations as we were doing. This is the first thing we have up to v minus 1, up to these many iterations we do for this relaxation, right? Next last iterations for word which if there is a relaxation happens, or we can call this one, if there is a relaxation, in that case we assume we will get to know by Bellman Ford algorithm there is a negative cycles, right? If there is a negative cycle, we return true, otherwise we take turn false. We can easily and if you are asked questions, so how can you tell me what is the path sort, as we this algorithm is what this algorithm is telling us to shortest path from yes to all other vertices. Yes, you can get it. how you can get actually v dot pi means what? V dot pi means you are reaching to v by a u, and then you go to you reach u from yes to on other vertex. Suppose u dot pi is means some other vertex w, means you are reaching to w, to then via w you are reaching to u. In that way you can figure out very easily. But at time complexity, if we talk about this Bellman Ford algorithm, is this line goes to up to, at most we can take this these many in the set of vertices which are present cardinality of that set, and this is nothing, just a v square, right? Now at most edges which are present in any dense graph which is v square, right? The instruction number of times executed is v cube, right? So and the worst case time complexity of this algorithm goes to order of v cube. I hope this is clear. Now we'll move to next algorithm. I think I will discuss next algorithms in the next lectures. So thank you for watching this video. If you find this video is helpful for you, please do like and comment below. If you see you find any problems to understand the lectures, you can comment. I will reply you. Thank you for watching this video.